In this video, I'll talk about what diffusion is and the difference between simple and facilitated diffusion across the cell membrane. First, what is diffusion? Simply put, diffusion is the tendency of molecules to move from areas of high concentration to areas of low concentration due to random movement. To visualize this, let's look at a simulation by David Blausch. On the left, I see particles moving randomly due to thermal motion. These could be water molecules, for instance. The red particle could be a solute molecule in the water. On the right, I see a trace of the path that the solute molecule is taken in the water. Notice that it doesn't have a single direction. It is constantly getting bounced around randomly by the surrounding water molecules. If I pause the simulation after a while, I see that the solute molecules ended up here. It didn't set out to get there. It's just where it ended up after getting bounced randomly around. If I reset and restart the simulation, I see that another solute particle that started in the same place moves in the same kind of path that the first one did, in this random bouncing path. But because their motion is random, they don't follow the same path or end up in the same place. If we started off with many solute molecules in the same place at the beginning, we would see them spread out to fill the box. In other words, they would move from an area of high concentration to areas of low concentration. This happens through the random motions of the molecules, not because they're actively trying to avoid each other or seek wide open spaces. To sum up, if I have two areas, one with a high concentration of solutes and one with a low concentration of solutes, and the solutes are free to move between them, then the random motion of the solutes and water molecules is going to result in a net movement of the solutes from an area of high concentration to an area of low concentration. In other words, as each of these guys randomly moves around, they're going to spread out until after some time they're evenly spread out between the two areas. The molecules here are moving randomly about just as before. The motion of individual molecules hasn't changed, but now molecules are randomly moving between the two sides at the same rate. They're moving in this direction from here to here and in this direction at the same rate. So the net movement between the two sides is zero. In other words, the system is in equilibrium. Now let's imagine that my two sides are separated by a membrane, like a phospholipid bilayer. And I start off with a bunch of O2 molecules in this side of the box. There's a bunch of O2 dissolved in water over on this side. So if I leave this for long enough, what's going to happen? So since O2 can diffuse across that phospholipid bilayer because it's a small nonpolar molecule, if I leave it for long enough, when I come back, these O2 molecules are going to be spread evenly on both sides. So it was just as like the case when this wasn't here, because these can diffuse through this membrane. And because there's nothing helping these O2 molecules diffuse across that membrane, this is known as simple diffusion. Let's imagine that I have a similar situation before. So I have my box of water and I have this phospholipid bilayer separating the two sides. Only now on this side, I've got sodium ions dissolved into the water. So if I leave this, what's going to happen? So keep in mind that these sodium ions are charged, and so they're not going to be able to diffuse easily through this phospholipid bilayer. So instead of spreading out into both sides, they're going to randomly move around just on this side. So they'll remain on this side of our box. So what happens if I insert a bunch of sodium channels into this membrane? Those sodium channels are going to allow these sodium ions to diffuse across this membrane so that given enough time, they'll become evenly spread throughout these two boxes. Because this sodium channel was facilitating the diffusion across the membrane, this is known as facilitated diffusion. Now I'm going to look at these two cases side by side. I'm going to look at the rates of simple diffusion, which I'm going to have over here on the left, and facilitated diffusion over here on the right, versus the concentration difference between the side over here and the side over here. So we're going to look at the rate of diffusion across this membrane as we increase the concentration over here. And I'm going to be looking at glucose for both cases. We have to compare apples to apples, right? Glucose to glucose for simple and facilitated diffusion. Now glucose is pretty large and polar, so a lot of the time when it hits this membrane, it's just going to kind of bounce off. It's not going to be allowed through. But every once in a while, it's going to be able to diffuse through that membrane to the other side. And if we start with 0 glucose molecules over here, of course there's nothing to pass across, so we're going to have 0. But if I increase the glucose concentration on this side, so that now I'm going to have more and more glucose molecules that hit, and most of them are going to bounce off, but let's say 1 out of every million glucose molecules that hits this is actually going to diffuse across the membrane. So as I increase the concentration difference, as I increase the glucose concentration over here, so the amount of glucose hitting this membrane, I'm going to increase how many of them are getting to the other side, like that. Then our case is a little bit different over on this side, because this time, when a glucose molecule encounters one of these carrier proteins, it does just what it sounds like. You can actually carry that glucose molecule across the membrane. So it has a much easier path across the membrane. So as long as there are glucose carrier proteins available to carry glucose, the more glucose I add, the more glucose is going to get carried through these proteins, and the faster diffusion is going to be. And that's going to increase a lot more quickly than it did for our other case. But then if I keep increasing it, a lot of the times when this glucose molecule bumps into a carrier protein, that carrier protein will already be busy. So instead of getting carried across the membrane, this glucose molecule is going to bounce off. But sometimes it'll still encounter an empty one, and so it'll get carried across. So that rate will still keep increasing as I increase my glucose concentration, but not as much. If I keep increasing it, then eventually all of these carrier proteins are always going to be busy. So as soon as this glucose molecule gets carried across, there's going to be one right behind it to take its place. So these are just going to be chugging glucose across that membrane as fast as they possibly can. In other words, there's no possible way for them to speed up how fast they're chugging that glucose across, even if there is more glucose waiting behind to be transported. So this rate is going to level off. So that's this effect right here, where your carrier proteins, or let's say you're delivering something via channels, are all full, and so they can't move things across the membrane any faster. So they're doing it at the maximum rate here. Remember, it hasn't stopped. It's here at the fastest rate of diffusion across the membrane. It's just not going to get any faster. Whereas with simple diffusion, and I've drawn it a little steeper than it really should be, increasing the concentration is going to keep increasing how much gets across, because it's not waiting for a carrier protein, it's just diffusing right across the membrane. But that increase is going to be really slow. And that diffusion rate is not going to be as much as the facilitated diffusion rate.